Hey there everyone, we're here today to look at solving a parallel circuit with resistors in it. We're going to take a look at how that's actually done using some of the laws that we know about circuitry. So here we are, we have our circuit, and this is a parallel circuit. We have our battery here, 3-volt battery, and as what makes this parallel, of course, is the fact that when electrons come out here, when they get to this junction right here, electrons can either go down this path or they can go up here to either one of these two resistors. And so we have our resistors here, 100 ohms, 200 ohms, and 300 ohms. So let's go ahead and start solving for things like voltage, current, and the total resistance. All right, so here we are. When I solve problems like this, I like to start off with a chart. It helps organize things, and we can put in the things that we know. For example, the first resistor is 100 ohms. The second is 200 ohms. The third is 300 ohms. Our battery is a 3-volt battery. Now the goal here will be to find all of the other voltages, will be to find all the currents in all of the circuit, and find the total resistance for the circuit as well. So to start out here, what we're going to do is we want to look if there's anywhere we can apply something like Ohm's law. Now Ohm's law can be applied in a vertical fashion here. If we see anything in here, that any column that has two things we know in it, we can find a third. And in this case, I'm seeing that every column only has one item in it. So this is going to mean that we can't use Ohm's law. So the next thing we want to do is we want to look across here. We want to look for things that we can solve for. So I notice here in this column, or sorry, in this row, we have 3 of the resistors, and we can actually apply an equation to add our resistors together or combine our resistors to get the total resistance. All right, so here's our equation. Our equation is 1 over the total resistance equals 1 over the first resistor plus 1 over the second resistor plus 1 over the third resistor. So taking our resistors that we have, we're going to take 1 over the total equals 1 over 100 ohms plus 1 over 200 ohms plus 1 over 300 ohms. Now, anytime we want to add fractions, we're going to need to find a common denominator first. All right, so the common denominator for these 3 numbers is going to be 600, or I guess that is just one common denominator. So I'm going to write this out, 600 here and 600 here. All right, 1/100th is equivalent to 6 600ths. 1/200th is equivalent to 3 600ths, and 1/300th is equivalent to 2 over 600. When we add these together, I'm going to get, let's see, 6 plus 3 gives me 9, plus the 2 gives me 11 over 600. All right, and what I like to do to actually solve this out is kind of the operation I do, because again, my goal here is to get the total resistance by itself, but notice how it itself is in a fraction. So what I like to do is kind of reciprocate or invert the thing, and if I do that on one side, I need to do that on the other side. So when I actually do that, what am I going to get? I'm going to get RT over 1 equals 600 ohms over 11. And when I do the math for that, so I take 600 divided by 11, I get 54.5 ohms. All right, so we just found the first thing here. The first thing we did was find our total resistance, and we just found that out to be 54.5 ohms. Now, next thing we can do is actually, knowing that we have a parallel circuit here, we can actually apply something about Kirchhoff's voltage law, which basically says that the voltage in a series circuit, in a parallel circuit, is going to have to be the same. So basically, I'm going to have 3 volts here, 3 volts here, and 3 volts there. So step 2 was to actually apply here this idea of the voltage law, which is going to tell us that the voltage is the same. Now, if you notice what happened here, by knowing this 3 volts here and the 100 ohms, this actually allows me to find the current here, here, and here. So some people would argue that this is actually a little bit easier than the first step we did in our case. And I would say too that this is certainly a good first step, is to actually start with this and then find your currents. And once you find your currents here, we can actually then use another one of Kirchhoff's laws to find our total current. And we'll talk a little bit about that in just a moment. So the next thing I'm going to do here, step 3, is to solve for the current here in resistor 1. I'm going to rearrange my Ohm's law as I equals V over R. In this case, the voltage is 3 volts and the resistance is 100 ohms. When I do the math, I'm going to end up with 0.03 amps. And to speed things along here, I'm not going to show the work for these, but the work will give me this amount here and 0.01 amps there. I'll come back at the end of the video and put the work back in, but for now, let's just do that. Okay, so after we found all the currents in all these places, the next step here, and I guess in this case will be our last step, is to actually find the total current. Now, we know that there's something called Kirchhoff's current law, which basically says, in fact, let me go back to my picture. So what this means for us is that when we take a look at the current in all of these 3 resistors, if we can add them together, we get the total current for the actual circuit as well. So when I do that, I get 0.055 amps. Now another method you could have done to actually find this is, you can see that we have our resistance here and our voltage there. We could have applied, again, Ohm's law in this form to actually find this very same thing. Now, I mentioned a while back that putting these together here sometimes presents a problem for some people when they don't like to work with fractions. If you take a look, if we hadn't found this as our first thing, by knowing our voltage here and our current here, we could actually rearrange Ohm's law and find this resistance. And this could have been our last step had we not had already found it. So again, what we have here is Kirchhoff's current law, which, as we have current that comes out of this this negative terminal, comes up here to this junction. Some of the current goes down this path, but some of it also goes down this path. Basically, what Kirchhoff's law says is that whatever comes into this junction right here is going to equal the sum that comes out of these two. So if I have, let's say, 1 amp coming in here, this might split off as half of an amp here and half of an amp here, or possibly 1 amp comes in here and maybe we get 3/4 of an amp here and 1/4 of an amp there. But in the end, if we take a look at all of these resistors as they come back together here, they're going to total up to give us the total current for the entire circuit.